Hello and welcome to this talk. My name is Alejandro Jaramillo. I am from the Instituto de Ciencias de la Atmósfera at UNAM in Mexico. Today, I'm going to talk about the combined influence of the QBO and ENSO on tropical cyclone activity over the North Atlantic Ocean. To start, we can have a look at the intense 2020 Atlantic hurricane season. This plot shows the tracks of all the tropical cyclones of that season. We can see that that season was quite active. And this is the list of all those tropical cyclones that were intense enough to get a name. But pay attention, the season was so active that even there are Greek letters as names, since the list of available names for that season was exhausted. This shows us that this season was very active in terms of the number of tropical cyclones. But is this the same for all seasons? All the years that active? If we compare the 2020 season on the left with the 2015 season on the right, it is clear that the 2015 season was very calm compared with the 2021. Why is that so? Why are there more years that are more active than others? It is well known that the tropical phenomenon is the main responsible of this behavior. There is a phenomenon in the tropical Pacific Ocean associated with anomalies of sea surface temperature that has a great impact on the interannual variability of climate. This phenomenon is known as El Niño-Southern Oscillation, ENSO, with its very distinctive phases of El Niño and La Niña. These anomalies are also coupled with the large-scale circulation, especially with the Walker circulation, like this figure that shows El Niño case, and this figure that shows the case for La Niña. ENSO creates conditions that might help or inhibit atmospheric convection around the world. For example, during El Niño, the conditions are unfavorable for the development of tropical cyclones in the North Atlantic basin, while during La Niña, the conditions are more favorable. This explains a lot of the difference in the season activity year after year. For example, if we explore the cause associated with tropical cyclones in the Atlantic basin for Mexico, we see a clear difference in the magnitude of the cause and in the regions affected. That motivated a previous study on the socioeconomic impacts associated with tropical cyclones in Mexico, where we include the local vulnerability in the analysis. This paper is open access and you can find it by using the QR code below. Also, in the description box, I will provide the link for this paper. Now, if we study a variable like the accumulated cyclone energy, ACE, that is kind of a measurement of the activity of the tropical season in terms of wind speed. And if we compare this ACE along with an ENSO index, we can see that some seasons seem to be very active even though with El Niño conditions. This is the case, for example, for the very active 2005 season. This suggests us that ENSO is not enough to understand cyclone activity in the North Atlantic. So now we must ask what other tropical phenomenon could be important for the modulation of cyclone activity in the Atlantic Ocean basin. At least, from an empirical point of view, this phenomenon must fulfill at least two basic conditions. First, must have an ENSO-like period, and second, must have impacts on tropical atmospheric convection. We found that there is a well-known phenomenon that perhaps might fulfill these conditions, but this phenomenon is not located in the troposphere. In fact, it is located in the stratosphere and corresponds to an oscillation in the zonal winds at these high levels, as this animation shows. This phenomenon is known as the Quasi-Biennal Oscillation, the QBO, that propagates in the stratosphere down to the tropopause. An important question that raises is how this phenomenon in the stratosphere might influence the convection. To understand the how, we must study the structure showed by Collymore et al. That present us with this very interesting plot that show us that in the interface between the stratosphere and the troposphere, the QBO interacts in a way that can modify the height of the tropopause. This might sound something trivial for our question, but is not trivial at all. This, in fact, is a very important point since the tropopause is like an upper boundary for the convection. So if we have a higher tropopause, there are better chances to have taller deep convection. So going back to Collymore et al., on the left we can see that the QBO in its west face, the tropopause is in the tropics tend to be low, while in the subtropics the tropopause is higher. On the right, the case for the QBO in its east face shows the opposite behavior. This will be very relevant for our problem, but going back in time, the idea of the influence of QBO on tropical cyclones is not new at all. In fact, it was the great Bill Gray, perhaps the first to propose a relationship of QBO and tropical cyclones. Bill found that when the QBO was in its west phase, the Atlantic tropical cyclone activity was greater than when the QBO is in its east phase. Also, that the most intense Atlantic hurricanes tend to be in years with QBO in its west phase. These observations allow him and his group at the Colorado State University to use the QBO as one of the predictors in their seasonal forecast for many years. But a very important work by Camargo and Sobel found something discouraging. They found that although there is a statistical significant relationship between the QBO and tropical cyclones in the Atlantic from the 50s to the 80s, that relationship is not longer present in later years. This may ask ourselves how it is possible that the QBO show some influence in the past but not anymore. Perhaps what is happening is something similar to the interference of waves, where waves can interact to enhance their effect or to completely destroy the signal. So, the QBO might have an impact on tropical cyclones, but its influence has interference with ENSO. Therefore, we cannot study independently both the QBO and ENSO if we want to know what's going on. To study this combined effect, we used a hurricane track database and we created a track density. With this track density, we explore the mean difference between different combinations of QBO plus ENSO. When we consider both effects together, a pattern started to emerge. Even for the same ENSO phase, there are clear differences if the QBO phase is considered. Despite the limited amount of data, the differences are statistically significant for some regions marked with crosses. Here, we show the figure with all the combinations for this track density anomaly, and we did the same analysis for an ACE density with similar results as is shown in this figure. Both of these figures suggest that the combination of El Niño plus QBO East and La Niña plus QBO West are like the opposite phases of each other. So it is clear that there is a combined effect between ENSO and QBO, but how this relates with the ideas of Collymore et al.? That's the big question. So here we have the plots of the anomalies in the tropospheric height for each phase of ENSO and QBO independently. It is clear that El Niño and the QBO East tend to decrease the tropopause in the subtropics, while La Niña and the QBO West does the opposite. So if we combine both ENSO and QBO, there will be combinations that will try to produce higher or lower tropopause and combinations that cancel each other. We also try to estimate a measurement of the tendency of the circulation in the cross tropopause region, shown in red in this figure, together with the anomalies in the tropopause height in black. Graphically, this figure is a little bit hard to understand at first sight, but if we focus on both the most contrasting combinations, we can create a cartoon like this, where we are trying to suggest the kind of circulation tendencies in the cross tropopause together with the tropopause high tendency. The interesting point appears when we compare this figure with the original figure of Collymore et al., showing great similarity between them. This suggests that this cross-tropospheric mechanism is acting, but the interference of ENSO makes it hard to see in observations. Only when we consider the effects of ENSO and QBO together, we are able to see the pattern. So, the ideas behind this talk and other analyses are published in this paper that is open access, so please go to this QR code. You can freely download this paper, and also you will find a link in the description box below. So the take-home message are that considering the constructive and destructive interference of different macroclimatic phenomena is essential to understand interannual climate variability. In particular, understanding tropical atmospheric convection in the Atlantic Ocean requires considering the joint effect of ENSO and QBO. And if we want to build seasonal models of tropical cyclone activity, we must consider the effects together of ENSO and QBO. So I want to acknowledge the partial funding by UNAMPAPIT that made this work possible, and thank you very much for watching. Please contact me on this email, or you can find me also on Twitter. Thank you very much.